All right, so let's come back. So let's talk about the huge patch management. So before this patch, actually, we are saying the page size is usually 4 kilobyte, but actually the page size can be larger than 4 kilobyte. And sorry. Okay, so actually the page size can be larger than 4 kilobyte, but in current Intel CPU, it only supports 4 kilobyte, 2 megabyte, and 1 gigabyte. And there is a reason. So the reason is like this. When we are saying we are going to increase the size of the patch, then we say if the page size is 4 kilobyte, then we are going to use the last 12 bits to address or to locate the data in this 4 kilobyte, right? But if I split from here, the 21 bits, so the 21 bits means 2 megabyte, right? So this is the reason why Intel supports 4 kilobyte, 2 megabyte, and 1 gigabyte. Because if we split here from 2 megabyte, so we only need to translate, we only need to traverse 3 tables, right? Because after 21 bits, they are pointing to the same patch. Then we only use this. We can use these 21 bits to address the data position inside this 2 megabyte patch. And the same thing for 1 gigabyte. So if it is 1 gigabyte patch, actually we only need 2 patch table walk. Then we can stop here. Then for these 30 bits, they represent the data inside 1 gigabyte patch. Okay, so maybe you already find out some interesting things. So when the size of the patch grows, actually it can reduce the number of patch table walk. So one of the main goals for increasing the patch size is to enjoy the benefit of fewer patch table walking. Because if you are using 1 gigabyte, then you only need to walk 2 patch table. Compared with if you are going to walk in 4 patch table, you can save like half of the time. And because virtual translation, virtual to physical memory translation, usually you need to do for most of the instructions. So it affects a lot for the CPU performance. If you can only set half of the patch table translation numbers, then you can boost like twice of the CPU like performance here. Okay, so this is the goal for this kind of huge patch management. Okay. And before talking about huge patch management, I think we need to do one thing is actually when you are using a huge patch, it doesn't only benefit the patch table translation, it also can increase the TOB reach. So here is a definition for TOB reach. TOB reach is the TOB size times the patch size. So you can think about the amount of memory accessible from the TOB. So because the TOB size is fixed, so for example, in prior Intel CPU, you can only do like 1,186, something like that, TOB entries in the CPU. So if the patch size is 4 kilobyte, so let's say if you can only do 1024 TOB entries here, then if your patch size is 4 kilobyte, then actually you can only reach out 4 megabyte of the memory patches. Okay, because one entry, one patch. So you have 1024 entries and each page size 4 kilobytes, so you can address it for 4 megabyte area. But if the same things, you have 1024 TOB, but now the page size is 2 megabyte, then you can address up to 2 gigabyte of the memory. So you will be you will largely increase the TOB reach. Okay, So it really helps for this kind of TOB rich things when you use the huge patch. And patch table work, I think, already point out these things. So let me give you an example. Actually, inside CPU, there is a TOB. And for regular TOB, you can see like a virtual address 0 point to the physical patch. Physical address 3, virtual address 1 will be translated to the PBF add like this. And this is for regular TOB. Oh, okay. It's okay. I'll show you later. Okay, so like this. The huge TOB will look like this. Virtual address 10 to 522. The reason like from 10 to 522 is because for 2 megabyte huge patch, it comprises 512 of the regular patch, right? 512 times 4 kilobyte equals 2 megabyte. So for this virtual address from 10 to 522, you can directly be mapped to physical address here. Then you can save a lot of the virtual address translation from TOB. Because if you are going to use a regular TOB to represent this, only this sentence, this line, you will need 512 of the entries here. Because here is 10 to 552. So there are 512 here. So for this, you need 512 entries in the regular TOB. Okay, so this is a good thing. But the bad thing, I think you already know, the bad thing is the virtual address and physical address should be in a continuous way. So for huge patch, the physical address should be continuous. I mean, for the 4 kilobyte, it's quite easier. But if the patch size is 2 megabyte, you need to have the 2 megabyte of a continuous physical address. It's quite difficult. I mean, for virtual address, it's quite simple because each process has their own virtual address. So you are going to find a continuous virtual address is quite easier. But because all the process share the DRAM, share the same amount of DRAM. So if you say I want a continuous 2 megabyte region, actually it's quite difficult. But if it is possible for you to do this kind of things, then you can get a lot of benefit from reducing the patch table working and then to increase the TOB reach. So you can greatly save a lot of for this kind of translation. Okay, so actually current Linux supports two kind of huge patch, I would say like promotion or like creations. The first one is using a library. So this library, huge patch TOB FS, it works more like a file system. This is a library that can back application, text, data, memory allocation, and share memory with huge patches. So for example, if in the compiling time, you already know you have a lot of memory and they are used for the continuous way. For example, you have a lot of global variable and they can be stored in the physical memory continuously, then you can use this library to allocate for them. Okay, but this is not easy for a runtime. So the thing is, if you are going to do a more runtime things, there is a things called transparent huge patch, and this is also supported by Linux. So a transparent huge patch, there are two different operations. One is called huge patch promotion, and the other is called huge patch demotion. Okay. So for a huge patch promotion, it's like this, because we say, hey, we are going to do a continuous 2 megabyte area in a DRAM. So 2 megabyte means you need 512 or 4 kilobyte regular patch, right? Because 512 times 4K is 2 megabyte. Okay, so usually if the data in the memory is not continuous, and maybe if sometimes your data required by this physical address is backed in a swap area, like in a storage, then you need to do a promotion. Promotion means you need to copy out the data from the memory and then from the storage, and then to combine them together inside a 2 megabyte continuous area. So they can become a huge patch. Okay, so the overhead will be super huge if, I mean, the good thing is if you are using memory allocation and you do really use this 2 megabyte area, then you don't really need to do this kind of promotion because you can directly allocate 2 megabyte area and you put the data inside, then we're done later. But when the system runs for a relatively long time and the system is in a high memory pressure, and you are saying, hey, I'm going to create one huge patch, like 2 megabyte, then there will be a lot of data movement, including from the memory and including from a storage device. You need to move from storage device, from the memory device, and then put them together in a continuous 2 megabyte area. So you can finish this huge patch. Okay. Okay, so I think that is enough for you to know about a huge patch. So that is all for the lecture 3. So let's move on to lecture 4. So lecture 4 will not be in your midterm, but it will be in your final. Okay, so your final actually will be from lecture 1 to lecture 5. So including the midterm part. Okay, so preparing for midterm is quite important because you can use in 2 places, midterm and the final. Okay, so first of all, let's come to look at this split view for the kernel. So this is the system call interface. So above the system call is applications. So under here are several hardware device, CPU, blah, blah. And between them, there is operating system Linux kernel. So from lecture 1 to lecture 3, what we cover is from process management, memory manager, and virtual memory, all these kind of things is here. This is before midterm. And actually, we're not covered here, like how to write the device drivers and those kind of networking things. We're not covered here. So for lecture 4 and lecture 5, what we will cover is from disk to block device for file systems and then to the file system part. So we'll cover all this path out. Okay. So first of all, let's talk about memory and storage. Oh, if you guys already took the memory and storage course last week, I think lecture 3 will be highly like the same things that you learn, but will be a little bit coarse grained because you learn is more details here there. So okay, let's get started. So for the memory hierarchy, the reason like we need memory hierarchy is we're going to balance the access time and cost. So look at the pyramid on the right hand side. So the bottom is the storage and the between is memory and a cache. So actually the access time for storage is from 50 microseconds to 1 milliseconds. And there is one best line is for CPU. So CPU instruction, each time it takes like 0.3 nanoseconds for a 3 gigahertz CPU. So if it is 1 gigahertz CPU, then it takes like 1 nanosecond here. Okay, so microsecond means like 1,000 nanoseconds. So millisecond is 10 to the 6 nanoseconds. Okay, so storage is super slow. And memory is a little bit faster because, oh, sorry, it's way more faster because memory is from 10 to 100 nanoseconds here. And then for the cache TOB, actually they are all SRAM-based device. So their asset latency will be 1 to 10 nanoseconds. So it is around another 10 times faster than the memory. Okay. Okay, so I think the gap is quite obvious here. So the top of the pyramid is super fast, the bottom is super slow, but the price is also on the reverse way. Storage is super cheap, but cache is super expensive. Okay, so this is the reason like you do not really see someone use the CPU SRAM to that it becomes a memory. Okay, because SRAM is super expensive here. And also the density is not allowed for SRAM to let it to grow to like gigabyte level. Okay, and storage, it has better density scaling. So you will usually see currently we have like 10 gigabyte of SSD or like several terabyte of SSD. They are all possible. But for memory, you are hard to see more than 64 gigabyte. Okay, so that is for that. And there is another thing is about the capability to absorb the CPU access. So this is just a funny thing to let you know. Actually, if you have a good CPU, like patch replacement things inside a CPU, then you have a CPU cache, it can usually absorb like around 90 to 99% of the CPU access. So there's only like 10% of the memory access there are only 10% of the instruction access will go to the memory. So among this 10%, there's around 90 to 99% will be absorbed by the memory. So there are only very few of the assets will go to a storage. So there are like 10 to the -4 of the assets will go to a storage. So usually like there are only one request among the 10,000 instruction will really go to a storage. So this is also the reason why we are going to build up this hierarchy, because even we have very few CPU cache, we can absorb that much of the CPU assets. So actually it is quite effective there. Okay, so even storage device is so slow, but actually if you have a good cache and memory design, actually there are only very few instructions will really need the help from storage device. Okay, so this is the cost-effective mode for this kind of memory hierarchy. So where's operating system execution time? Because operating system execution is just about when CPU running the operating system code, like the kernel function, those kind of things, right? So operating system execution is usually between the memory and storage. So it is around like 100 nanoseconds to 10 microseconds. So it depends on what kind of code you are running. You are running context switch, you are running scheduler, or like you are only switching from the kernel to user mode to do some very simple things. So it depends. So the range is quite huge here, but actually you'll be around 100 nanoseconds to 10 microseconds here. So because running operating system takes a little bit more time. So when the CPU is getting data from memory, usually CPU will use a load store instruction to directly get the data. So when CPU uses a load store instruction to get the data from memory, usually there is no involved from operating system. It doesn't really need the help from operating system. CPU can directly get the data from the memory. Okay. But if now CPU needs to get the data from storage, the story will be a little bit different because storage device is super slow. So there is some room for the operating system to do something. So for example, if CPU doesn't want to do too long of time, then CPU needs to run context switch, right? And context switch is kind of kernel code. So it takes some overhead, like around 1 microsecond here. But the good thing is the storage device usually takes like 15 microseconds. So even it spends 1 microsecond for running the operating systems, then you can set for another 49 microseconds. Then CPU can go to do any other process. It doesn't really need to wait here for the I/O completion. So those kind of patch fault handler, system call, those kind of things, they are related to the operating systems. Okay, so this is quite different for CPU to access both memory and storage. Their CPU is using different way to access the memory and storage. Okay, so actually when we talk about memory, actually there are different kind of data in memory. So roughly speaking, there are process data and file data. So the reason there are file data is because there is a thing called patch cache. So patch cache is if now you are going to read out a movie from your hard disk drive, and then if there is enough space of memory, then the movie will be cached inside the memory. So next time, maybe in a few, like 1 hour or 2 hours, you are going to access the movie again. The system doesn't need to get the movie from storage device. It can directly access from the memory, and you will get faster response time. Okay. So as we mentioned in the prior slides, CPU access the data in memory by using load store. But to be a little bit more precisely, actually, for process data, CPU access them by using load store instructions. But for file data, CPU access them by running the system call and I/O stacks. Okay, so even the file data is inside the memory, CPU will do some operating system stuff to manage the data. Because if the data is in the patch cache and the patch cache, even it is a memory, CPU will run the operating system to manage them. Okay, so when we talk about load store, when CPU is going to load store data in the memory, actually, if the data is not in the memory, then memory will raise a patch fault, and usually it's a major patch fault. Then there are several things that CPU needs to do. So CPU needs to run a patch fault handler to do the fault area check-in to know, hey, why there is a patch fault. And then if CPU knows, oh, it is because the data is still in the storage device, not in the memory, then CPU will run the patch swapping And because patch swapping takes too much of time, so CPU will run context switch to other process. So this is the flow for the process data. So if the data is in the swap area, like this path. So there is another path is about system code. So when we are going to rewrite the file, actually there's file IO, then maybe in your C code, you will write fread, right? So fread in the library, actually it will finally call the system code. So with this system code, there is another path to deal with it. So because this is a file related system code, so CPU will first check the patch cache to check about if there is a cache data already in the memory. If it is, then CPU will directly return the data required by the request. But if not, then CPU will access like the file system and then get the data to check about where the data is in the storage device. And then do the context switch. Okay. So after give you a brief introduction about how CPU access the like memory and data or like access the storage device, actually let's talk about what is data on memory storage device. So the data is a sequence of 0 and 1. For example, if there is an image, then if this is a binary image, then 0 means black, 1 means white. And if it is a grayscale, if there are 4 bits, sorry, if there are 2 bits, then 00 means a black one, and dark gray means 01, and 10 means light gray, and 11 means white. So each image can be represented by a sequence of 0 and 1. Not only images, but also the voice, the audio. So for the audio, for this signal, it can be sampled to several data points here. So if we use like 4 bits to sample for this signal, then you can see like maybe this 0111 means this peak and this 100 means this peak here. Okay. So this is how the multimedia be stored on storage device. Actually, there are still a sequence of 0 and 1. Then the thing is, but how to store this 0 and 1 in the storage device or memory device? So actually, device usually consists of material which can switch between 2 states stably. They can be memory or storage device. So the reason to switch between 2 states is because we are going to represent 0 and 1. So if one material can be switched between 0 and 1 stably, then it can represent one cell, no matter it's storage cell or memory cell. So later on, we will introduce hard disk drive and SSD. So hard disk drive, you can think about like it is about a magnetic field, like it is a parallel or anti-parallel. So it means 0 and 1. And for SSD, it means like the high voltage or low voltage. So inside the cell, if the cell is high voltage, maybe it means 1. And if it is low voltage, maybe it means 0, for example. And the same for DRAM. So DRAM using capacitor. So if the capacitor is charged, then maybe it means 1. And if it is not charged, maybe it means 0 because it is 2-stat. Okay. So there are also some new non-volatile memory like IRAM, PCM, and STT-MRAM. So all of them, they are using the switch between the resistance. So high resistance, that means like 0, and low resistance means 1. Okay, so they will use different kind of physics, chemistry, or like different kind of way to map the materials to show different high or low resistance. Okay. Okay, so we talk about like hard disk drive SSD, they are non-volatile. And DRAM, I think you already know it is volatile memory. So the difference between volatile and non-volatile is it possible to keep the data even when the power of the device is off? So DRAM is volatile. So when you shut down your computer, all the data on DRAM, they will get off. They will be disappear. But I mean, like hard disk drive, even you don't power for this hard disk drive, the data is still there. even for SSD, you carry your SSD over out of the power, the data is still inside the SSD. Okay. And there is another thing is called access granularity. So it is about the minimum rewrite size of each device. So if you still remember, I say for memory, we are using a byte addressable, right? So you can see like current memory device like DRAM, like IRAM, PCM, SERAM, when they are saying they are memory device, they are byte addressable. So they can be addressed to the granularity, to the byte granularity. Okay. The thing is, actually, SSD is like patch granularity. So the minimum granularity for SSD will be like 4 kilobyte to 16 kilobyte. So it is way larger than 1 byte. So SSD is not byte addressable. Okay. So hard disk drive, like we are using a sector, and it is around 512 byte to 4 kilobyte. So it depends. Okay. Okay, so there is a comparison table between all common non-volatile memories and storage device. So first of all, is a cell size. So cell size affects a lot, because if you are a larger cell size, it means it is hard to scale down the size for this memory cell to increase the capacity. So you can see like for SRAM, the cell size is between 120 to 200 F squared, and DRAM is 60 to 100 F squared. But if you compare to like NAND flash, or like, oh, there's no hard disk RAM, where NAND flash is 4 to 6 F squared. So you can image, actually, for the same like size of the device, NAND flash can provide you like several terabyte of the, oh, sorry, NAND flash is a SSD that you are using now. I mean, the details, like how it stores the data, they're all stored in the NAND flash. So for current SSD, it is possible to offer you like several terabyte of the capacity. But for SRAM and DRAM, for one SRAM and DRAM, actually you can only get like, for SRAM it is quite smaller, like several megabytes, so large. But DRAM, it is a little bit larger. It can become several gigabyte, but still DRAM cannot achieve like terabyte level. And the reason is because the cells for this device, like SRAM cells, so what for one cells, it is around 120 to 200. So it is kind of 30 times larger than the NAND flash cells. Okay, so for these NAND flash cells, it can downsize like 30 times smaller than the SRAM cells. Okay, and the reason is because the reason is depends on what kind of the circuit things they are using. For SRAM, they are using 6 flip-flops, and the DRAM is about their capacitor, so it is hard to decrease the cell size. So there are second thing is about the write endurance. So write endurance means like when you write several times to this device, how much of the write can be endured by this device. So 10 to the 16, you can image like the SRAM can endure like 10 to the 16, more than 10 to the 16 of the assets. So it is quite a lot. But if you look at like NAND flash, IRAM, PCM, actually those kind of non-volatile device, they can only provide like 10 to the 4 to 5 for NAND flash, and 10 to the like 11 for IRAM, these kind of things. So they are vulnerable. I mean, if you write like 10 to the 6 of the amount of data into the NAND flash, then the NAND flash will be worn out. So you can think about for each NAND flash cell, it can only endure like 10 to the 4 to 10 to the 5 of the write operations. Okay, so the reason for IRAM, PCM, those kind of, and NAND flash is because they are non-volatile structure. So usually for non-volatile structure, they are going to capture like electrons, or to capture some things inside the device without power. So usually there are some materials they will there to protect those kind of data, those kind of electrons to get off. So those kind of materials, they have their lifetime. So this is a reason for like NAND flash and IRAM, they have a little bit limited lifetime compared with others. And there's another important thing is, if you still remember this one, sorry, this one. So as we mentioned, we are going to, for the CPU cache, it needs to absorb like, it is possible to absorb like 90 to 99% of the assets, right? And memory, it is a little bit lower, like there's 10% here, and then inside is 10%, memory will absorb like around 90 to 99%. So you can think about, for the cache, it should have a longer lifetime because it should endure a lot of write in the cache. So if now you put your NAND flash in the cache level, and because NAND flash only have 10 to the 6 of the lifetime, so NAND flash can only endure 10 to the 6 to the assets, then NAND flash will burn out. Okay, but come back with, sorry. Okay, but come back with the SRAM. Actually, the SRAM can endure 10 to the 16 of the write. So SRAM has better capability to be as a CPU cache. Okay. So read and write latency also, it differs a lot, and we only show you at a prior slide. So let me just skip this one. So power consumption, like for the leakage power part, actually because SRAM and DRAM, they are volatile memory. So even there is no rewrite operations, DRAM, like their capacitor will drop, the capacitor level will drop. And SRAM actually the leakage power for their 6 flip-flop, I mean the stat inside will also change, even there is no rewrite operations. Okay. Okay, so for the dynamic memory part, actually we means like there is a rewrite operations. So how much energy are there for each read operation and write operations? So there's here. Okay. So I want to show you, like usually for some memory they show the asymmetry energy consumptions, which means like actually if there are different states, and when that's changed from one state to another state, usually that costs more energy. So rewrite, you can think about like, especially for write operations. Write operation will affect the state. So for some memory, just like SCT RAM, if it is 10 to 01 or like 00 to 11, actually it consumes different number, it consumes different energy. And also rewrite for the SCT, MRAM, those kind of memory, they consume different kind of energy to perform the read and write. Okay, so that is for the I/O performance part. So for the I/O device and I/O systems, let me give you a top-down overview about what happens here. So when the processor calls a system read or system write, so because read and write is a file-related system code, and inside the kernel, actually we'll first run a virtual file system. And then below the virtual file system, there are two paths. One is patch cache, because we are going to first check if the data in the patch cache or not. If it is, then we can return it. But if it is not, then the request will be sent to the mapping layer. So mapping layer, actually you can think about, it is the file system you know. So like ext4, beta file systems, and like those kind of different kind of like make file system, they are all in this layer. So in kernel Linux, actually you can support different file systems simultaneously. I mean, for one disk, you are going to use ext4. Another disk, maybe you are going to use exFAT, those kind of things. It is also possible. So mapping layer means like different kind of file system specific. And then we will come to the block IO layer. So like it will go to the block device driver, and then we'll send the request to the device. So inside the device, there are also firmware to receive the request from the block IO and block device driver there. So we will cover all from device, from device driver and IO layer, and also the file system. We will cover all of it. And for lecture, I think it's lecture 4, we will cover the last the bottom 3 one. And for lecture 5, we will cover the yellow part. So what you can learn from lecture 4 is about we will introduce hard disk drive and the variant of hard disk drive called SMR, and then a NAND flash-based solid-state drive. And then we will talk about how device drivers work. And if I remember correctly, maybe there is hands-on for a device driver. I think it's the third one. And we'll introduce what are device drivers and how to write a device driver. And because actually, in most cases, if you join like MediaTek, Realtek, those kind of design house company, in most cases you need to write the device drivers. So just let you know what is device driver. And block I/O layer. So we will talk about what is block I/O layer here, and maybe there is like how to merge and collect I/O operation, and what is an I/O operation, and how I/O scheduler works here. So let's first talk about the device part. So actually, you will learn 2 different kind of device. One is hard disk drive. So right hand side here. Left hand side here is the hard disk drive. So there are several components inside the hard disk drive. If you open the hard disk drive, you will see something like this. So there is an actuator and actuator arm. So this arm is going to read out the data or like to write the data. So the data they are stored on this plater. So there are several stacks of platers here. I mean, there are several stacks here, and there are several platers. So there is a spindle bundle those platers together. So actually the spindle will rotate it. And this is the reason why when you power on the hard disk drive, you hear the noisy voice. It is because the spindle is rotated. So there's a little bit noisy there. And the good thing for the hard disk drive is cheaper than SSD usually, and high reliability. Because if you store the data inside the plater, actually, if you place there, you can put the data there for a super long time. And even you write it, even you read it, there is not damage for this kind of platers. So the only things you will hurt the platers is if you drop the hard disk drive on the floor, or if you use a super strong magnetic to affect the data stored on the platers. So only those outforce will change the data stat inside the plater. Otherwise, if you normally just read and write, the life of the plater is super long. So on the other hand, for the SSD, the reason that it is called SSD, the solid state drive, is because if you look at the left-hand side again, because the spindle will rotate it, and there is a moving head here. The head will move from here to here to read out the data from the platers. So there are all moving components inside hard disk drive. But on the right-hand side, SSD, actually, there is no moving components because there is only the controller cache and then the NAND flash memory chips here. So there is no moving parts. So this is the reason why SSD is so light, and there is no sounds when you are using the SSD, because controller just like a CPU, and they are using this kind of circuit things to read out the data from the NAND flash memory chips. Okay. So the good thing is about it has faster performance. The reason is there's no moving heads. So if each time you need to rotate the platers, you're going to move the arm to get the data, because they are all mechanical things. So it takes long time to get the data. But if most of the things you can get by circuits, I mean, you choose a voltage value, and then you send the voltage value, and then you read the current. Actually, it will be way faster than the mechanical moving part. And there is no vibrations or noise. So it is because there is no moving part inside. Lighter, smaller, and support random access better. So the reason is, if you look at the left-hand side, if the data is stored on the platers, so if you are going to do the sequential access, it is easier to do. But if you are going to do the random access, then you're going to move the arm from here to there to there to there. So you need to wait for the plater to rotate to the right position, and then you need to move the arm to the right position to serve for this kind of random access. So it takes a lot of time for hard disk drive to do the random access. But SSD, actually, it can support good random access. Okay, so I think after our midterm, we will start from introducing a hard disk drive. So thank you so much. See you guys.